Good morning. Now this is class 7 of the module nuclear reactions. Now here we will learn about scattering and reaction cross sections in terms of partial wave amplitudes. So here we are considering Z axis as the direction of incident beam, and suppose that the incident beam is a plane wave of the form e raised to I k z, and let its momentum be p is equal to h cut k, and suppose that the outgoing particles are represented by spherical waves. Why? Because it will be very easy if we use the notation of spherical waves. So we are representing that incident spherical wave as a superposition of many spherical waves, and it is represented by equation 1. This equation you might be familiar when you have learned spherical harmonics. Now here A is a normalization constant. Here JL of KR is the spherical Bessel function, and they are actually solutions to the radial part of Schrodinger equation in a region very far from the target where the nuclear potential vanishes. Now the angular functions, that is PL of so they are represented by equation number 2. Now this expansion of incident wave is called partial wave expansion. Here each partial wave corresponds to a specific angular momentum L. Now this procedure will be valid only if the nuclear potential that we are considering is central. Suppose that the particles have a momentum p, let it interact with impact parameter b, then relative angular momentum will be LH cut is equal to PB. Here, from here you can directly write this B as L lambda cut. Lambda cut is nothing but lambda by 2 pi, and this is called reduced de Broglie wavelength. So let that be equation 3. Now when this specific angular momentum, that is L, suppose that its value lies between h cut and 2h cut, and let the cross section that we consider is a ring of inner radius lambda cut and outer radius 2 lambda cut, so its area will be 3 pi lambda square. Now we are dividing the interaction area into a number of zones. Suppose that each zone corresponds to a specific angular momentum L with area this one. So we are assuming that the maximum impact parameter that is the impact parameter is supposed to be maximum, and L value is also maximum at the value R by lambda cut. Momentum will have maximum value. Then the total cross section is represented by equation 4. It is denoted by the letter sigma. So this particular expression for total cross section sigma is valid for an effective interaction radius of R plus lambda cut. Now here what we have assumed is that the wave is very far away from the target nucleus. Now what will happen if the wave for the same situation, that is if the wave is far from the target nucleus, the JL of KR, that is we have already said what it is spherical Bessel function. It will have the following expansion. It is enough that you just mention this equation only, no need of writing this. Then the expression for incident wave function is given by equation 6. This you will have to write. Now the first term in bracket involving e raised to minus I kr represents incoming spherical wave converging towards the target, whereas the second term having e raised to plus I kr represents outgoing spherical wave emerging from the target nucleus. So this minus sign denotes incoming wave which is going into the target, and the positive sign represents outgoing wave that comes out from the target. Now the superposition of these two spherical waves will give you the final expression for the plane wave. That is, it can affect only outgoing waves in any of the two ways. That is, either there will be a change in phase or there will be a change in amplitude. The change in amplitude suggests that only few particles coming out than they are going in. That is, a number of particles coming out will be less when compared to number of particles coming in. That means there is a change in amplitude. That means there will be a loss in the number of particles. So that is, if the number of particles coming out is less than the number of particles going in, then you can expect a loss in the number of particles. Then definitely that will be a change in amplitude. Now the reaction that's discussed can be either elastic or inelastic. Then here we are introducing a complex coefficients eta L into the outgoing term, that is e raised to I k r term of equation 6. Then equation 6 will reduce to as given in equation 7, just a slight modification. This represents superposition of incident and scattered wave. That is, incident wave plus scattered wave will be the net wave function. Okay, now in order to find the scattered wave, we have to subtract equation 7 from equation 6. Then once you subtract, you will get the expression for scattered wave as given by equation 8. Now these are just few expressions. Equation 9 represents the scattered current density. Equation 10 these two equations are very important that you will have to mention. So here we are considering only elastic scattering. Okay, if we are considering in other process, then there will be a slight change in the above given equation 12. So if there are other processes in addition to elastic scattering, then equation 12 is not valid, because modulus of eta L will be always less than 1. Now we group all those processes together as reaction cross section sigma r. Here to find that cross section, that is to find the reaction cross section, first what we have to do is we have to find the rate at which particles are disappearing from the channel with the wave number k. That is, we have to find the difference between incoming current density and outgoing current density using respectively the first and second terms of equation 6. Then you just mention that sentence and you can write directly this equation. The final expression for reaction cross section will be given by equation 14. Now the total cross section including all process will be scattered cross section plus reaction cross section, that is sigma SC plus sigma R, that will be the total cross section sigma T. So equation 15 also is very important that you have to write. Now the results that we get from here is, it is possible to have elastic scattering in the absence of other process. That is if modulus of eta L is equal to 1. However, to have reactions without also having elastic scattering, that is any choice of eta L for which eta are not equal to 0 for a given partial wave automatically gives is sigma SC not equal to 0 for that partial wave. That is, it is enough to write like this: if it is possible to have elastic scattering in the absence of other process, that is if eta L equal to 1, then equation 14 vanishes. It is enough that you mention this sentence. Then if the this also you have to write, if the particles are removed from the incident beam, creating a shadow behind the target nucleus, incident particles will be diffracted into the shadow. Then second point, for a black disk absorber in which all partial waves are completely absorbed up to L is equal to R by lambda cut and unaffected for, that is absorbed until the value L is equal to R by lambda cut and unaffected for the value L greater than R by lambda cut. And just mention these equations 16, 17, 18. So the total cross section is twice the geometrical area. Okay, and this one you can skip, no need of mentioning this up to this. Just write about the scattering and mention the results. Okay, thank you.